Hello, welcome to another module in this massive open online course. So, we are looking at example problems in the Z transform, right, to understand the various properties and applications of the Z transform. So, let us continue that discussion to do our final example. So, we are looking at example problems. We are looking at example problems for the Z transform, okay, and let us look at the last example, example number 9, that is consider, we are looking at, we will look at a difference equation. Consider the LTI system described by the constant coefficient differential difference equation, correct? Difference described by the difference equation. We are looking at a difference equation, and the difference equation is given as yn minus y by 2 yn minus 1 plus yn minus 2 equals xn. Now, what we are interested in finding is, for this we want to find the impulse response and the transfer function. So, first we want to find the transfer function hg and the impulse response for the above system. Remember, hg, this is the transfer function, and hn, this is the impulse response. Okay. And this can be done as follows. If we consider the Z transform, on both sides, and then what we have is, if you take the Z transform of yn, let us say we denote the Z transform of yn by yz minus. Now, the Z transform of yn minus 1, remember this is the delayed version of yn, therefore, the Z transform of yn minus 1 will be yz times z inverse, that is yz times z raised to minus 1. Okay. So, minus 5 by 2 yz times z raised to minus 1 plus the Z transform of yn minus 2, which is naturally yz into z raised to minus 2, and this is equal to Z transform of the right, Z right hand side is xn, so Z transform is xz. So, this implies that basically we have something very simple, we have yz times 1 minus 5 by 2 z inverse plus z minus 2 equals xz, which implies yz by xz yz by xz equals 1 divided by 1 minus 5 by 2 z inverse plus z minus 2, which is equal to z square divided by z square minus 5 by 2 z plus 1, all right, and this is basically your y z by x z, which is the transfer function. Okay, so this is basically the transfer function, that is z transform the impulse response. Transfer function of the LTI system. Now, also h z, now remember h z equals z square by z minus 2. So, the poles are z equals 2 comma half, because we can write this as, now h z can also be simplified as observe z square over z minus 2 into z minus half. So, there are two poles at z equal to 2 and z equal to half. These are poles, each pole has multiplicity 1, all right. So, these are simple poles and the poles are z equal to 2 and z equals half. Okay. So, now we are going to perform the partial fraction expansion to find the inverse z transform. So, consider now h z over z. So, we use the partial fraction expansion. For the inverse z transform, and this is equal to well, z over z minus 2 into z minus half, and let us say we express this as c naught over z minus 2 plus c 1 over z minus half. Now, we consider this, let us also be consider a system that is a causal. Okay. Consider a causal system. So, causal system implies that remember, causal system implies that it has to be a right handed signal. Therefore, ROC is of the form, it has to be greater than equal to 2, since 2 is the maximum magnitude of the poles, correct. So, since we have a causal system implies that the impulse response is a right handed signal. For a right handed signal, the ROC will be of the form magnitude z is greater than R max, where R max is the maximum magnitude of the poles of the transfer function, all right. So, causality implies that the ROC is of the form magnitude z greater than 2, and which is basically also equal to R max, remember. Okay. So, this is equal to R max, maximum of the amplitude of the poles of the transfer function. Now, here, now once we have done that, now it is relatively easy to find C naught. We have done this several times before. So, C naught, it is a simple pole. So, z minus 2 times h z over z evaluated at z equal to 2, which is basically your z over z minus half evaluated at z equal to 2, which is basically 2 divided by 2 minus half, that is 3 by 2. So, this is equal to 4 by 3. Now, similarly, C1 equals z minus half into h z over z evaluated at z equal to half, which is equal to z divided by z minus 2 evaluated at z equal to half. So, that is basically half divided by half minus 2 equals half divided by minus 3 over 2. So, that is basically, so C1 equals minus 1 by 3. And therefore, what we have is Hz over Z equals you have 4 over 3 divided by 1 over Z minus 2 minus 1 over 3 times 1 over Z minus half, and therefore, Hz itself equals 4 over 3 into Z over Z minus 2 minus 1 over 3 into Z over Z minus 2, and we have the ROC magnitude Z greater than 2 implies this is causal, of course, right, implies this is a right handed signal. Implies is a right handed signal, which implies that this quantity h of n, that is the impulse response h of n, is simply 4 by 3 2 raised to n u n minus 1 by 3, of course, this is z over z minus half minus 1 over 3 times half raised to n u n. That is basically your impulse response of the LTI system described by the causal LTI system described by the differential equation. Okay. Described by difference equation described by the difference equation given in the problem. All right. So, basically what we have seen in this problem is we have seen a difference equation, all right, an LTI system described by a difference equation, how to find the transfer function from that, and how to invert the transfer function, correct, to find the impulse response, that is the response of the LTI system in that response of the LTI system to an impulse in that time. All right. So, we will stop here and look at other aspects in the subsequent modules.